Let us begin gently and at the largest scale imaginable. Tonight we are thinking about cosmology, about global spacetime, and about some of the more advanced structures that appear when we try to understand the universe not merely as a collection of objects, but as a single geometric whole. We are no longer looking only at a planet, or a star, or even a galaxy. We are trying to think about the universe itself as a spacetime, as one vast mathematical object with structure, curvature, history, and causal organization. It is worth pausing already on that thought. In ordinary life, when people speak about the universe, they often imagine a very large container filled with matter. They imagine galaxies, gas, radiation, perhaps dark matter, all sitting inside some immense emptiness. But the mathematical viewpoint of relativity invites us to think differently. It asks us not to imagine a container first and content second. It asks us to understand that the geometry of space-time itself is part of the physical story. The universe is not just things in space. The universe, in the relativistic picture, is space-time together with matter and radiation, bound into a single geometric and dynamical system. This is one of the most profound changes in perspective in all of mathematical physics. And yet, even though the scale is enormous, the basic language remains the language we have been slowly building. Manifolds, curves, metrics, curvature, geodesics, causal relations. Cosmology is not a departure from geometry. Cosmology is geometry at the largest possible scale. It is the study of the global shape, evolution, and structure of spacetime itself. Let us pause and reflect. When we study smaller or more local questions, geometry told us how clocks behave, how rulers compare, how light travels, and how free particles move. In cosmology, the same kind of ideas remain with us. We still ask what a metric means. We still ask how distances and durations are encoded. We still ask how matter influences curvature and how curvature influences motion. The difference is that now we are applying those ideas to the universe as a whole. At such enormous scales, it becomes useful to introduce symmetry assumptions. This is not because the universe is perfectly symmetric in every detail. Clearly it is not. There are stars here, empty regions there, clusters of galaxies in one place, void in another. On small scales, the universe is messy and structured. But on very large scales, when one averages over enough detail, a remarkable simplification appears. The universe seems roughly the same from place to place, and roughly the same in every direction. These two ideas are so important that it is worth repeating them slowly. Roughly the same from place to place means homogeneity. Roughly the same in every direction means isotropy. Homogeneity says that no spatial location is singled out in a large-scale description. Isotropy says that no direction is singled out. These are not statements about every small region or every local observation. They are idealized large-scale geometric principles. They tell us how to model the universe when we zoom out so far that local irregularities fade into the background. This is one of the recurring themes of mathematical physics. Symmetry is not merely aesthetic. Symmetry makes structure visible. Symmetry reduces complexity. Symmetry reveals what kind of geometric model may plausibly describe reality. So cosmology begins with a large act of abstraction. We stop focusing on individual bodies and instead ask if the universe is homogeneous and isotropic on large scales, what kind of spacetime geometry is compatible with that? This question leads us to one of the central models in relativistic cosmology, the expanding universe described by what is commonly called the standard cosmological metric. Let us approach this slowly and intuitively. Imagine that at each moment of cosmic time we take a kind of spatial snapshot of the universe. In each such snapshot, space is distributed in a way that respects large-scale homogeneity and isotropy. That already imposes strong constraints. It means the spatial geometry at a given cosmic moment must be highly regular. But the universe is not static. Those snapshots are not identical. As time passes, the spatial geometry changes in an organized way. This change is encoded by a single central idea, the scale factor. The scale factor is one of those concepts that becomes clearer the more softly we say it. It is not an extra object floating in space. It is not a force. It is not an invisible wind pushing galaxies outward. It is a way of describing how the spatial part of the metric changes with cosmic time. In simple language, it tells us how the effective distances between far-separated comoving points in the universe evolve. That phrase, too, deserves gentle unpacking. A comoving point is not a little rock drifting through pre-existing space. It is better thought of as a point tied to the large-scale cosmic flow, a point that participates in the general expansion. So, when we say the distance between such points changes, we are not imagining galaxies racing through a rigid background in the ordinary sense. We are saying that the geometry of space itself changes with time. The metric evolves. Space is not static. Space-time has a built-in temporal development. It is worth repeating, in relativistic cosmology, the universe expands not because everything moves through an unchanging stage, but because the stage itself changes geometrically. This distinction is subtle, and listeners often drift toward the older picture of motion through fixed space. So let us pause and reflect. Suppose you paint dots on the surface of a balloon and gently inflate it. The dots separate, but not because each dot is crawling across the rubber under its own power. They separate because the surface itself changes. Now, every analogy has limits, and this one should not be pushed too far. But it captures a useful intuition. In cosmology, the large-scale increase in separation is a feature of geometry. The metric changes. Distances evolve because the structure that defines distance evolves. This is why the expanding universe is inseparable from the metric description of spacetime. Expansion is not an extra story added after the geometry. Expansion is part of the geometry. And so, when cosmologists speak about the universe expanding, they are speaking in the language of spacetime structure. The scale factor provides the simplest global measure of that expansion. If it increases, large-scale distances increase. If it changes more rapidly, expansion accelerates in a certain sense. If it changes more slowly, expansion decelerates. The cosmic history of the universe is written into the temporal evolution of this geometric scale. Now from this viewpoint, a very natural question arises. If the geometry of space changes while light is traveling through it, what happens to the light? This brings us to cosmological redshift. We have already learned in simpler settings that light plays a special role in spacetime. Light traces null directions. Light reveals causal structure. Light allows observers to infer geometry from what reaches them. In cosmology, light also carries an imprint of the large-scale evolution of the universe. As light travels across an expanding spacetime, its wavelength is stretched. The crucial point is that this stretching is not best understood as merely a standard Doppler effect, though there is a relationship at a certain level of approximation and interpretation. More deeply, cosmological redshift is geometric. The light is propagating through a spacetime whose metric evolves. The expansion of the universe affects the light wave itself. It is worth repeating because this idea is easy to hear but harder to hold onto. Cosmological redshift is not just a story of galaxies flying away through fixed space while emitting light in the ordinary way. Rather, the light moves through expanding spacetime, and the wavelength stretches along with the evolving geometry. The redshift is therefore a witness to global structure. It is evidence that spacetime itself has a large-scale dynamical character. Let us pause and reflect. This is one of the beautiful features of cosmology. We do not directly touch the geometry of the distant universe with our hands. We infer it through light. By studying light that has traveled enormous cosmic distances, we read off information about the structure and history of spacetime. Observation becomes geometry. Astronomy becomes, in a deep sense, the remote sensing of metric evolution. And once again, the central lesson returns: the universe is not a static box. The universe is a spacetime whose geometry evolves, and the light we observe bears the marks of that evolution. Now whenever one speaks of the universe as a whole, and especially of its evolution, difficult questions appear. If the universe expands, what happened earlier? If the geometry changes, can one continue this description indefinitely into the past or future? Are there limits to the classical spacetime picture? These questions lead us toward the topic of singularities. The word singularity is often used dramatically in popular writing, but mathematically it should be handled with care. A singularity is not best understood as simply a point where some quantity becomes large in a coordinate system. Coordinates can mislead. Coordinates can fail for superficial reasons. A genuine singularity is something deeper. It indicates a breakdown in the classical geometric description itself. One of the most important ways to express this breakdown is through the idea of geodesic incompleteness. Let us say that slowly. A spacetime is geodesically incomplete if there exist freely falling trajectories, or light-like trajectories, that cannot be extended indefinitely, even though, from the perspective of the intrinsic geometry, one would expect them to continue if the spacetime were complete. In other words, the path simply runs out. Not because a coordinate chart became inconvenient, but because the spacetime description itself reaches a limit. This is a powerful and subtle concept. It shifts our attention away from coordinate formulas and toward the global structure of the manifold, a metric. A singularity, in this sense, is not necessarily a point inside the manifold that we can circle on a map. Rather, it is a sign that the manifold with its Lorentzian geometry fails to provide a complete arena for physical trajectories. It is worth repeating, singularities are not merely badly chosen coordinates. They are statements about the limits of the classical theory. This is why the singularity theorems are so profound. They are global geometric results. They do not depend on a particular coordinate system. They show, under broad conditions related to causality, energy content, and gravitational focusing, that certain spacetimes must be geodesically incomplete. These theorems say that the breakdown of the classical description is not an accident of notation. It is built into the global logic of the geometry. Let us pause and reflect. A singularity theorem does not usually tell us what the singularity looks like in a naive pictorial sense. It tells us something more structural. It says that the spacetime cannot be continued in a geodesically complete way once certain global conditions are met. So the theorem reveals a limitation of classical general relativity. The geometry is extraordinarily powerful, but it is not the final word everywhere. There are regimes where the classical description reaches its boundary. This is especially important in cosmology, because when we trace the expanding universe backward in time, classical relativity suggests that there may be an initial singular behavior, not simply as a dramatic explosion inside pre-existing space, but as a limit of the space-time model itself. The classical geometry points backward toward a boundary of applicability. And here it is worth saying something calming and precise. To say that the classical theory breaks down is not to say that thought ends. It means only that a different or deeper theory may be needed. Mathematics has brought us to the edge of one framework. That edge is itself a meaningful result. From singularities, let us move gently into another global idea, causal structure. Causal structure is, in some sense, the skeleton of spacetime. It tells us what can influence what. It organizes events not by arbitrary coordinates but by the light cones and time-like possibilities built into the Lorentzian metric. If one event can send a signal to another, that is a causal relation. If no signal traveling at or below the speed of light can connect them, then they are causally separated in an important way. This organization becomes especially rich when we stop thinking only locally and begin thinking globally. Over large scales, the causal structure of a spacetime can reveal horizons, inaccessible regions, singular behavior, asymptotic limits, and the overall architecture of influence. To help us visualize this, mathematicians and physicists use Penrose diagrams. These diagrams are wonderfully clever. They compress infinite regions into finite pictures while preserving the essential causal relationships. That is the key idea. They do not preserve ordinary distances in the Euclidean sense. They preserve causal structure. Light rays still appear in a controlled way, and the relationships of influence and inaccessibility remain visible. It is worth repeating that such diagrams simplify without trivializing. A Penrose diagram is not a casual sketch that ignores the mathematics. It is a compressed geometric representation designed precisely to retain what matters causally. It allows us to see, in one finite picture, how infinity is approached, where horizons lie, how singular boundaries may appear, and which regions of space-time can communicate with which others. Let us pause and reflect. Infinity is difficult to imagine. The future of a time-like observer, the faraway behavior of light rays, the global reach of causal curves, all of these become unwieldy in ordinary coordinates. Penrose diagrams are a way of taming that difficulty. They translate a vast or even unbounded space-time into a compact picture without discarding the causal bones of the geometry. So once again, geometry gives us not only equations and abstract structures, but visual ways of understanding the deep organization of space-time. Now let us turn to a slightly different but related perspective. So far we have often spoken of spacetime as a four-dimensional whole. But there are many problems in physics and geometry where it is helpful to think of spacetime as built from a family of spatial slices evolving in time. This brings us to hypersurfaces, slicing, and the initial value problem. A hypersurface, in this context, is a three-dimensional slice inside the four-dimensional spacetime manifold. You may think of it as a spatial snapshot, though the phrase should be handled gently, because what counts as space and what counts as time can depend on the geometric setup and the observer. Still, in many important situations, one can choose a family of space-like hypersurfaces that foliate a region of spacetime. In simple language, spacetime is decomposed into successive layers of space. Why do this? Because it allows us to reframe Einstein's theory as a kind of evolution problem. Instead of treating spacetime only as a completed four-dimensional object, we can ask, if suitable geometric and physical data are given on one spatial slice, how does the spacetime develop from that data? This is the essence of the initial value formulation. It is worth repeating. One gives appropriate initial data on a hypersurface, not arbitrary data but data satisfying certain geometric consistency conditions, and then one studies how the spacetime evolves. In this way, general relativity acquires a dynamical aspect very much in the spirit of other evolution theories, though with much more subtle geometry. Let us pause and reflect. This decomposition into space plus time is not merely a technical convenience. It reveals something important about the interplay between local and global structure. Local geometric data on a slice can determine, at least in principle, a whole spacetime development. So the theory connects instantaneous geometric information with extended four-dimensional history. This is another theme worth keeping near us. Spacetime can be studied both as a whole and as an evolving family of space. The two viewpoints complement one another. One emphasizes the full geometric object. The other emphasizes development from initial conditions. And now, as we move further into advanced structures, symmetry returns once again. Symmetry in spacetime is not merely decorative. A symmetry is a geometric invariance, a way in which the spacetime can be transformed without changing its essential metric structure. In intuitive language, a symmetry is a motion of the spacetime that leaves the geometry unchanged. The infinitesimal generators of such symmetries are called Killing fields. Since we are avoiding formulas, let us describe this slowly. A Killing field is a vector field that represents a continuous symmetry of the metric. Flow along that field, and the metric remains invariant. So a Killing field expresses the fact that the geometry looks the same in a certain direction of transformation. It is worth repeating because this is a deep and useful idea. A Killing field is not merely an arbitrary vector field drawn on the manifold. It is a geometric witness to invariance. It tells us that some aspect of the spacetime does not change under a corresponding continuous transformation. This could be a time translation symmetry, a rotational symmetry, or some other invariance depending on the spacetime under study. And why do we care so much about symmetry? Because symmetry and conservation laws are intimately linked. When a spacetime has a suitable symmetry, quantities associated with motion along geodesics can be conserved. This is one of the great organizing principles of mathematical physics. Invariant geometry gives rise to constants of motion. Rotational symmetry relates to angular momentum. Time translation symmetry relates to energy in appropriate settings. Spatial translation symmetry relates to momentum where such symmetry exists. But here we must be gentle and precise. In general relativity, concepts like energy and momentum become more subtle than in flat spacetime or classical mechanics. There is no universal simple global notion that works in every curved spacetime without qualification. The availability and meaning of conserved quantities depends strongly on the geometric context, especially on symmetry and asymptotic structure. Let us pause and reflect. This subtlety is not a flaw. It is a sign that geometry has become primary. Conservation laws are no longer imposed from outside. They emerge from invariance properties of the spacetime itself. So once again, the mathematics of spacetime teaches us to think relationally. Quantities that seemed absolute in simpler theories become contextual and geometric. From symmetry and conservation, let us move to another elegant tool of global geometry and field theory, differential forms. At first, differential forms can seem abstract, but their purpose is deeply natural. They provide a coordinate-free language for integration, orientation, flux, and global balance laws. When one wants to integrate over curves, surfaces, hypersurfaces, or full spacetime regions in a way that respects the geometry, differential forms become extraordinarily useful. It is worth repeating that integration in spacetime is not merely a matter of adding up little rectangular boxes as in elementary calculus. The geometry may be curved. The coordinates may be distorted. The submanifolds over which we integrate may be tilted, curved, or dynamically defined. We therefore need a language of integration that is invariant and adapted to geometry. Differential forms provide exactly that language. Let us say a little more. A differential form is an object designed to be integrated naturally over oriented geometric pieces of the appropriate dimension. Orientation matters because integration is not just magnitude, it also has direction, or more precisely handedness and sign structure. When we speak of flux to a surface, or the integrated content across a boundary, or a conserved current passing through a hypersurface, forms express these ideas cleanly. This is why they are so central in relativistic field theory. Fields often have natural integral statements associated with them. Conservation laws are often expressed globally by relating what happens inside a region to what passes across its boundary. Differential forms make these relationships precise and coordinate independent. Let us pause and reflect. Local tensor calculus tells us what happens infinitesimally. Differential forms and their integration help us pass from the local to the global. They connect pointwise geometry to large-scale statements. They allow us to express flux, circulation, conservation, and invariant volume in a unified way. So once again, a pattern emerges. Local structure and global structure are not separate worlds. They speak to each other. The metric tells us local measurement. Curvature tells us local bending. Causal cones tell us local influence. But then global notions arise: total flux, global causality, singularity theorems, cosmic expansion, conserved quantities from symmetry. The mathematics of space-time is rich precisely because it weaves the local and the global together. And that brings us naturally toward a broader reflection. We have now moved through a long arc of ideas. We began with the large-scale geometry of the universe. We saw why symmetry assumptions such as homogeneity and isotropy become powerful in cosmology. We considered the expanding universe and understood expansion as a statement about the evolving metric, not merely about objects moving through fixed space. We saw how cosmological redshift reveals the stretching of light by expanding spacetime, and thus how light becomes evidence for global geometry. We then turned to singularities and learned that they mark not just coordinate trouble, but the limits of classical spacetime description, often expressed through geodesic incompleteness. We explored causal structure as the organization of influence in spacetime and Penrose diagrams as compressed representations that preserve that causal organization even while taming infinity. Then we shifted viewpoint and considered spacetime slicing, hypersurfaces, spatial snapshots, and the initial value problem. We saw that Einstein's theory can be viewed dynamically as the development of geometric data. After that we returned to symmetry, meeting killing fields as generators of geometric invariance and conservation laws as their deep companions. Finally, we considered differential forms as the natural language of invariant integration, orientation, flux, and global balance in relativistic geometry. It is worth repeating that all of these topics belong together. At first, they may seem like separate chapters. Cosmology, singularities, causality, hypersurfaces, symmetry, forms. But they are all aspects of one central mathematical vision, spacetime as a geometric structure whose local and global properties determine physical possibility. Let us pause and reflect more deeply on where this mathematics leads. One natural continuation is Lorentzian geometry as a subject in its own right. This is the mathematical study of manifolds with metrics of spacetime type, emphasizing causality, geodesics, global hyperbolicity, singularities, and rigidity phenomena. In this field, one studies spacetime not only because it describes physics, but because it is a beautiful and subtle geometric category with its own theorems and challenges. Another continuation is mathematical cosmology, where one studies specific large-scale models, perturbations of those models, stability questions, cosmic horizons, and the global consequences of different matter contents and geometric assumptions. Here the geometry of the universe becomes a precise mathematical laboratory. Yet another continuation is quantum field theory in curved spacetime. This subject asks what happens when quantum fields are placed on a classical curved spacetime background. It does not yet quantize the geometry itself, but it already reveals something extraordinary. Curvature, horizons, and causal structure can affect quantum phenomena in profound ways. So even before full theory of quantum gravity, the union of geometry and quantum theory begins to produce deep insights. It is worth repeating that the mathematics of spacetime is both rigorous and physically profound. This is not one of those situations where geometry is only metaphorical. We are not saying that the universe is sort of like a curved surface in some vague poetic sense. We are saying something much stronger. In the relativistic framework, geometry is the structure of the theory itself. The metric is not decoration. Causality is not analogy. Curvature is not literary language. These are the actual mathematical ingredients through which gravitation, cosmic expansion, light propagation, and global structure are described. That is a remarkable achievement of human thought. And perhaps one of the most soothing aspects of it is the unity. So many phenomena that once seemed disconnected are gathered into a single language. Motion, gravity, time, light, cosmology, singularity, symmetry, conservation, integration. All of them become aspects of geometry or manifolds with Lorentzian structure. Let us pause and reflect one more time. If you have drifted a little during this lecture, it is perfectly all right. The central thread is simple enough to return to. The mathematics of spacetime begins with the idea that events form a geometric structure. Spatial relativity teaches us that space and time are bound together. Differential geometry teaches us how to speak about manifolds, metrics, curves, curvature, and tensors. Einstein geometry teaches us that gravitation is encoded in spacetime curvature. Cosmology teaches us that this geometry can describe the entire universe. Global methods teach us that causal organization, singularities, horizons, and conservation laws are not merely local effects, but expressions of the full structure of spacetime. That is the whole arc. And it is worth repeating in even softer words. Space and time are not separate backgrounds. They form a geometric unity. That unity is measured by a metric. The metric determines causality and motion. Curvature expresses gravitation. Matter and geometry interact. On cosmic scales, symmetry simplifies the picture and leads to models of expansion. Light reveals the expansion through redshift. Global theorems reveal the possibility of horizons and singularities. Slicing methods reveal dynamics. Symmetries reveal conservation. Differential forms express integration and flux in invariant language. All of this belongs to one mathematical world. As we come to the end, let us gather the ideas into one slow, unifying summary. Cosmology asks us to think of the universe itself as a spacetime. To do this, we use geometry at the grandest scale. Homogeneity and isotropy give us a clean, large-scale model. The expanding universe is then understood not as matter rushing through a fixed void, but as a changing metric structure. Distances evolve because geometry evolves. Light traveling through this evolving geometry is stretched, and this geometric stretching appears to us as cosmological redshift. When we analyze spacetime globally, we discover that some classical models contain singularities, understood not as mere coordinate accidents, but as genuine limits of the classical description, often revealed through geodesic incompleteness. We also discover that spacetime has a causal architecture, a deep organization of influence and accessibility, which can be visualized through Penrose diagrams that compress infinity while preserving causal truth. To study spacetime dynamically, we slice it into hypersurfaces and pose an initial value problem, linking spatial data to four-dimensional development. To understand invariance, we study symmetries through killing fields and see how conservation laws arise from geometric structure. To integrate naturally over curved regions and boundaries, we use differential forms, orientation, and invariant volume elements tying local calculus to global statements. And from all of this emerges one enduring lesson. Geometry is not merely a convenient language for space-time theory. Geometry is the content of the theory. The mathematics is not placed on top of the physics from the outside. The mathematics is the inner form through which the physics becomes intelligible. So as you let these ideas settle, perhaps the most restful thought is also the deepest one. The universe, in this theory, is not built on a hidden rigid stage behind appearance. The structure is the appearance, and the appearance is structured by geometry. To understand spacetime is to understand that measurement, causality, curvature, expansion, and global form belong to one coherent mathematical vision. Let that unity remain with you. Let the words slow down now. Spacetime is geometry. Cosmology is geometry at the scale of the universe. Expansion is geometric change. Redshift is light bearing witness to that change. Singularities mark the edge of the classical picture. Causal structure orders what can affect what. Hypersurfaces let us study development. Symmetry reveals invariance and conservation. Differential forms carry local information into global integration. And the whole subject, from special relativity to Einstein geometry to cosmology and beyond, forms one continuous mathematical landscape. That landscape is rigorous. It is subtle. It is physically profound. And above all, it is unified. Let us end there, with that sense of unity.